Okay, beyond least squares. If you look into the literature, about 99 point whatever % of the data analysis done in physics and in most other fields is done with the least squares. Least squares are great. Invented by Gauss 200 years ago, they turned out to be computationally extremely convenient. You could do a lot of math with paper and a pencil, which is great in the times where you had no computer. And there is actually also strong support by the law of large numbers that if you have a superposition of many probability distributions with some nice properties, you in the end always have a normal distribution. So those nice properties led to the result that the data analysis in the scientific community is more or less done by a least square approach. So, which means that we assume Gaussian errors, which can also be nicely justified using MaxEnt if we have the occasion value of noise 0 and some variance, and then we end up with a likelihood here. And if we now estimate the mean value, we get this nice equation where the data enters, the uncertainty of each data point, and a prefactor, which is essentially given by the variance. If you look at that formula, in the estimate, only the uncertainties of the individual data points enter, nothing more. That's great because that's very convenient. You can write down the solution of many estimation problems straightforward. But this result should be really disturbing because in your estimate, the true scatter of the data does not appear, only the supposed uncertainty. So that means that any transformation of the data about mean does not change the estimate and the uncertainty of the estimate. So let's assume we want to estimate the center point of this data cloud and give some uncertainty. We can do that quite easily, and we're happy with that result. However, using this transformation, we get exactly the same result for the red data cloud. Although looking at that, it's immediately obvious that the uncertainty should be quite different. When you look into the equations, then it turns out that this property is very particular for the least square estimation with the Gaussian distribution of the data points. So if you do Gaussian estimation, you should be pretty sure that the data really obeys a Gaussian distribution. Otherwise, you're in trouble. It's like you're using properties of a circle, but in reality, you have ellipses. You can be way off. So, making a quick jump, there's a very prestigious group in physics, the co-data group, and this is an interdisciplinary panel of experts which every 5 to 10 years derive the best estimate of all our physical constants, like elementary charge of E, Planck's constant, and some more obscure ratios. And this is a very complicated, difficult task, because if you think about it, if you want to measure a quantity, let's say a magnetic field, you rely that you have a certain current. Of course, this current is derived by some other basic properties. So what you end up is a huge nonlinear network of relations between the quantities you want to estimate. So that makes life complicated. And in addition, if you look at the best data you can get worldwide for those basic quantities, in this case it's the gyro-magnetic ratio of the proton, then you see that if you look at the values and the uncertainties, there appears to be a certain mismatch. You have relatively small alphas over here, even smaller ones here, but those two data clouds do not coincide. Okay, so you're in trouble because looking here at the data, you immediately notice a Gaussian distribution is highly unlikely to hold here. However, and that's the bad thing, is the co-data group applied least squares, and the best estimate in that case was a value which coincides neither with this cloud of data points nor with that one. That's very bad, and if you have looked closely, in this term of the variance, each data point, no matter how far outlying it is, reduces the uncertainty of the estimate. So if you add some points beyond the moon, your estimate is having a smaller uncertainty. That's that. Okay. Considering that data, and given that those basic constants are the quantities which are measured with the highest effort all over the world, I think it's fair to conclude that deviations from a Gaussian probability distribution have to be expected in real physical measurements. There have been approaches in the past how to deal with outliers. There's a nice paper, Seaver, 96, West, 98. Essentially, those approaches state, okay, we have a number of data points which belong to the distribution we have prescribed, and a number of outliers which have a very broad distribution. Those mixture models are pretty successful, but I'm not going to address those here. If you look into reported data, then it's quite likely that the uncertainty estimate is not fully correct. Why most people are interested in presenting new results, good data, and the uncertainty estimate is something which very often only the referee requests. And then you just come up with some rule of thumb. Okay, let's say plus minus 10%. That's good enough for government work. Okay, and then of course you have all those small experimental inaccuracies. Okay, given this background of information, why sticking to a Gaussian distribution, which is very peculiar? Why not generalizing the Gaussian distribution by using a different exponent alpha instead of settling on alpha equals 2? Okay, we can do that, and we can see how this one performs. Here a few shapes for different exponents of alpha. So the solid thick line is the standard Gaussian for alpha equals 2. If we increase alpha, which would mean that the tails are even faster decaying, we get those shapes. And if we go to alpha equals 1, which is essentially a two-sided exponential, we get this shape, should be right here, and then we can be even more extreme with very heavy tails using the square root of alpha. That's fine, and we proceed from there on. Now we have an additional parameter. If we want to perform estimates about probability of the data, given some mean value and uncertainty, we have to marginalize over alpha, which immediately raises the question, which phi over alpha? It is definitely bounded because nobody would claim that the uncertainty decays faster than, let's say, alpha equals 10. Even 2 is in most cases highly unlikely. Jeffreys prior cannot be applied here because of the absolute values. So we have a singular Fisher matrix, and looking at the, let's say, strong inequality between moving from alpha equals 1/2 to alpha equals 1 compared to alpha equals 4 to alpha equals 8, flat prior is also clearly ruled out. So what shall we choose there? And here we used an approach by Zellner. We used a prior which maximized the information distance between the prior and the posterior. That's very close to what Berger and Bernardo are advocating. Use the prior which has the minimal influence. So I'm not fully supporting this approach, but here we used it. For that, you essentially need to compute the information matrix, which is given by integral over the data space, P of data times log P of data, and if you do the math, you end up with a prior which looks like that, between 0 and some upper bound alpha. Okay, now we have all the ingredients. Yes?
So does that mean that in order to choose the prior, you must first already know the likelihood of the data that you've received after?
You mean that you have to know the data points you are going to measure later?
Yeah.
No, because this integral is over all possible
Oh,
data.
I see. I see. Okay. Thank you. Sorry.
Okay, so that would be one approach. Another approach is relating to the fact that in the previous generalized Gaussian, we still had the fixed measure of uncertainty sigma. However, this fixed measure does not exist in reality. We only have an estimate, our best estimate for the uncertainty of the data. So we can encode that, saying that we have a point estimate of sigma, and this point estimate is maybe wrong, but we have done our best to specify that, and then the principle of MaxEnt tells, okay, this scaling factor omega obeys an exponential distribution. Then, to derive our probability distribution for the data given some mean and our point estimate, we have to marginalize over this omega, and here we have our sigma integral with the delta function. This integration can be done quite easily, which in fact only replaces the sigma by s over omega, and then this 1 over omega can be analytically integrated out, and you get this little bit nasty looking formula. Indeed, it looks really nasty. Okay. But this is the key factor. You have an exponent 1 over x squared, and x is essentially the distance between the model value and your data point, scaled by the point estimate of the uncertainty. So if we now plot this term for single data point, then we can compare that with the standard Gaussian approach. The dotted line is the standard Gaussian, and you see it's a little bit broader in the center, but decays much faster compared to the marginalized Gaussian, which has heavy tails. Indeed, the tails only decay like 1 over x squared. Having a second look at the formula, it appears a little bit disturbing because x is the difference between the data and the true value, and so can be 0. So here we have then 1 over 0, again, again, again. But if you do expansion, then all the singularities nicely cancel, and the whole term behaves nicely like 1 minus 2 times x squared. So here we are safe. Okay, having now two different approaches to handle non-Gaussian, possibly non-Gaussian errors, we might jump into a data set which has been used by the co-data group, and those are 8 data points which were used to derive Newton's constant of gravitation. So here you see the 8 data points with respective uncertainties, and here the results for least square, that's here, so that's a Gauss. Then for the generalized Gauss, dashed line here, and for the marginalized Gauss. If you look at the values, of course they coincide quite nicely, except okay, the uncertainty in the last digits. The least squares approach, of course, is always symmetric. The generalized Gauss has slightly heavy tail towards negative values, as well as the marginalized Gauss. Okay, so that means, given that data point, our approach slightly stronger values those points over here. So saying that there's a small chance that the true value of the Newton's constant of gravitation is a little bit lower than the estimated value. Okay, but
those points don't seem to have error bars.
they are pretty small within the symbol size. Okay, now does the data support the use of least square fit, we can look at the burden ratio, which is essentially the measure of chi-square divided by the number of data minus 1. And if everything is nice Gaussian, we would expect a value around 1. Here we get 2.35. Okay, that's bad. So what did the co-data group do? This ratio is not 1. So there must be some non-Gaussian effect. So let's increase our estimated uncertainty by a factor of 10. Why 10? Why not 20 or 5? Okay.
Experts.
Yeah, those are the experts. Exactly. So that's bad. But here we can do better because we can estimate actually which exponent in the generalized Gaussian would be mandated by the data. And this is given here by the solid line. And you see that for true Gaussian distributed data, you should be around 2. But here it nicely centers around 1. So that means that the deviation are much stronger than Gaussian distributed data would indicate. As I pointed out in the beginning, essentially you can create mock data sets just by appropriate scaling around the mean value. And we did that here for 3 different merge ratios. And you see, if we do that, here the ratio would essentially say, okay, chi-square fit or least square fit would be perfect. We still get a pretty broad distribution for alpha instead of, okay, it should be closely centered around 2. One possible explanation could be that we have a relatively large spread because the number of data points is only 8. So that was what we're going to check next. We created additional mock data sets with the same birth ratio of 1, and then computed the posterior distribution for alpha. And you see, starting with 8 data points, where you have this very broad distribution, if you just accumulate data, you, in the end, have a distribution which is nicely centered around alpha equals 2. So here we see with around 50 data points, we can really identify if our data set is coming from a Gaussian distribution or not. Also, the uncertainty of the estimate is has been going down. Okay, so that means that we have really pretty strong evidence that the data used for the estimation of Newton's constant of clarification are not Gaussian. Okay, now outliers are always present, and in those one-dimensional examples I've shown you, it's pretty easy to spot an outlier. That's the point which is the far most to the left and to the right. That's an outlier, we move that to C. But what do you do if you have a high-dimensional data set? There's no way to spot an outlier. So you need some automatic procedure, and in principle, all I've shown so far is not really restricted to one dimension, but it would be quite nice to see how those 3 approaches behave if there is really an outlier present. For that purpose, we added in fictitious additional data point with the open solution shown here, and then we just move this data point from the left to the right and evaluated how the estimated mean value was changed by that. As it's well known, the least square approach is linearly sensitive to those deviations, which means that if you have an outlier which is sufficiently far out, your estimate is completely off. Okay, so this is the straight line here. For the generalized Gauss, we have the dashed line. It's pretty sensitive in the center, and then the influence of the moving data point on the mean estimate is being reduced. However, that's not good, because what we want to have is, if a point is clearly out, we want to have that the influence of this data point is going towards 0, and that's exactly the behavior we see for the marginalized Gauss. We have a pretty high sensitive sensitivity in the center, and then in the case of uncertainty, it's 0. Exactly the behavior we want to have if there are outliers present. So on that basis, I would say the marginalized approach has some benefits. We can do the same approach also to higher dimensional multivariate data sets. Here we see the posterior distribution for the elementary charge and Planck's constant for measurement of the Josephson constant, Toussaint constant, and we see it's non-Gaussian because then we would have elliptic shape, but deviations from that. And with the same formalism as before, we estimated the values of those constants and compare that with the least squared estimates, and we see in the elementary charge our least squared computation is plus minus 30 in the last 2 digits, but marginalized Gaussian also plus minus 30, and the co-data value is plus minus 40. So pretty good agreement. The same for Planck's constant. So here we could be very happy with that, but if you look closely, there's something surprising. As I told you before, if you add additional data points in a purely least square sense, the uncertainty can only be reduced. So we are still puzzling by using the data given in the reference of the co-data group. We obtain plus minus 30, and the co-data group obtains plus minus 40. Usually the standard explanation was, yeah, we are including additional correlations between the parameters, but this cannot be the explanation, because if you include additional data in the least square sense, you always reduce the uncertainty, no matter what you do. So at that stage, we have to say we do not really know what the co-data group did at that point. Okay, so coming to the conclusion, and Philip is already waving the last minute sheet. Both the generalized Gaussian and the marginalized Gaussian take into account deviations from the assumed distribution, and the GM approach is slightly better with outlier robustness. So balancing all the different approaches, I strongly recommend for the evaluation of experimental data to use the GM approach, which is not really much more complicated than a standard least square sense if you have a computer available. One topic to be addressed just for completeness, we haven't, for the GM approach, is using a Gaussian distribution with a marginalized uncertainty. What is going, if that, so the issue is, are there any benefits if instead of using a Gaussian with a marginalized error, we use a generalized Gaussian? And maybe, and that's my personal opinion, I think, then we're approaching the results of mixture modeling. Thank you very much.
I'm not fully understand your method, but a new parameter alpha is introduced in your generalized Gaussian distribution. I was wondering, how do you estimate these new parameters? Would you say that again?
The alpha parameter.
Yeah, alpha.
Yeah. So, for inferences about the data, we just marginalize over the alpha parameter. So in that case, we do not need to estimate that because we take into account all possible values. However, for this plot, yes, the probability of alpha given D, you essentially have to integrate to marginalize over the mean value, but that's a pretty standard procedure in Bayesian probability theory. So you just get rid of parameters you do not need by marginalization. I can show you the 2 lines of equations. So essentially you introduce the parameter, And since it's a kind of nuisance parameter because you do not really need it for further inference, then you marginalize over it. So it's just integration. So the upper line, to get rid of this additional parameter, you have to integrate over it, weighted by the prior alpha and this likelihood term. The likelihood term was given on the slide before. So essentially, this is a one-dimensional integral which is not really complicated.
I was, of course, the choice of a Gaussian is always somewhat ad hoc. Generalizing the Gaussian to this particular family of generalized Gaussians. My question is, can you say a little bit more about why you choose this family, this alpha?
Yes. Let's say you want to choose a family which includes the Gaussian. And generalized Gaussians are pretty popular because with the exponent alpha equals 1, it's in conventional statistics the poster child of underlay label Rover's estimation. We choose that family because it has a pretty broad applicability and it contains all the special cases we were interested in, like alpha equals 1, alpha equals 2. On the, let's say, if you, use a different function class, which appears here, if you do that, and use a slightly different prior for P of omega, you end up with a class of student T distribution, which is also pretty broad. What you essentially want to have in your function class is the possibility, the property that the tails of the distributions are heavier than the Gaussian distribution, because this is exactly the point where reality violates our.
Surely, but in the case when you're estimating, say, Planck's constant or gravitational constant, there is also some physical input in, for example, the fact that these constants are by definition positive, which means that to have a Gaussian distribution which extends to minus infinity is not realistic physically speaking in the first case. So you might also want to either to go over to the case where you're not estimating these constants what their logarithms, or you want to use family distributions which are cut off from next to
let me, so you're raising a very interesting point. Let me go back to my first slide. What this distribution describes is the statistic of the noise. It's not the statistic of the parameter. The parameter itself is positive. However, those distributions are addressed and if only the property of the noise, so the distortion of the measurement. They have nothing to do with the parameter itself.
But the measurements could also never yield negative values.
Of course, if you measure 5 Kelvin and your measurement is giving you 4.5 Kelvin, you're off by minus 0.5 Kelvin, so you get a negative deviation. So measurement errors by more or less, if you do a careful measurement, then the mean value of your noise should be 0. Otherwise, you have a kind of systematic deviation, which automatically implies that you have positive and negative contributions. But it's a very important issue that one has to be very explicit that those likelihood distributions are in almost all cases addressed for the noise statistics, not on the parameters. If you want to do model comparison, for example, later on with the parameter, yes, I completely agree with you. Then one should include that the parameter is positive and has some upper value which is pretty well established, and then a different prior comes into play, and then you need a different function there. But this is completely irrelevant here.
Well, hey,
tail of the noise would still go negative. It would be non-existent. But that's a very small amount.
That's one of the arguments, let's say, against the Cauchy distribution for noise, because there you have pretty strong contribution of outliers very far off, and I completely agree. However, here with the alpha exponent, we still have an exponential decay, so this does not occur. However, in the marginalized approach, yes, it's a 1 over x squared decay, and that allows for pretty large deviations.
Well, I had another question. In one of your initial slides, you had data that looked more like a sum of Gaussians.
You mean that?
Yeah. That would look more like sum of Gaussians to me. And I think you said at the end that you're heading in that direction as well, right?
Yes, so the mixture approach to describe data, yeah, that's...
So what happens when you get a mixture, a bimodal mixture? What happens then?
You mean if...
Shouldn't they go back and examine the experiments and see why?
Of course, but this data is already censored, and all the experiments which have some doubts have already been excluded by the expert panel.
Logically, that doesn't work.
Okay, if you look into the history of the co-data group, it's quite nice, because in '86 they published a paper that shifts in some of the constants were so large because they had deleted a data point in '72, which later turned out to be correct, and the other ones were false. And 2 pages later, they state that now they delete some other data points which appear to be outlying. And okay, but
okay.
Oh. Would it ever be useful to introduce another parameter on top of the alpha for generating the pattern tails in generalized, which provided for skewness? In other words, something like a generalized skew normal distribution. Would that ever be useful in situations where the noise could be considered to be?
So, like kind of edgeworth expansion or so, could be if you, let's say, could argue that the noise or your uncertainty would somehow be asymmetric. I can consider that there are situations where this may be useful, and but under normal circumstances, this is not very often occurring. So I can imagine that if you're going close to absolute zero, then you say, okay, I have more contributions by environmental fluctuations which raise the temperature instead of increasing it, and then the fluctuations would be clearly asymmetric. And then, yes, you should not use a symmetric distribution for that. But let's say, so far I have rarely run about those situations.
I guess that's the case of knowing your problem and setting up coordinates. On that one, you might want to measure recipient temperature or log temperature or something, and just take it all together. My point was rather that the tails that you ended up with looked more or less squared. So it might actually be natural to just start with the Cauchy and go from there, rather than starting with the Gaussian, except you'd never convince the experts.
This either.
Oh, so let's say we also and already did that, not for that problem, but yeah, also Cauchy works surprisingly well, and that would be a kind of second recommendation. If you do not want to fiddle around with additional parameters, just use Cauchy, and you are also quite secure against surprises. However, usually then the uncertainty margin you have to deliver is increased because the probability distribution of noise does not exclude large outliers, And that's something the experimentalists do not want. They say, oh, I did this experiment so carefully, and now you are coming and claiming that the uncertainty is this big. Are you crazy? I'm using good old least squares and get a factor of 4 better, and then I get it published. Yeah, so that's from a practical point of view. But if you want to be robust against outliers, Cauchy is a pretty good approach.
I have used it professionally.
Any more questions?
Okay, let's thank Guido again.